All right, folks, so I wrote a lot of stuff already. So I told you that you'd get all of the secret knowledge at the end of this semester. I didn't tell you at the beginning of the semester. I had to like stick it out all the way. So you now get the secret knowledge. You're gonna get two secret knowledges today. You're gonna figure out why E equals MC squared. And you're gonna figure out what the fuck special relativity has to do with all of this electromagnetism bullshit that we've been learning about all semester. So let's just really quickly recap that part there that I wrote, because I can tell some people maybe haven't memorized how to use tensors. That's completely natural, right? You haven't used tensors regularly. So I introduced them as this idea of a four vector. That is, we could say X, Y, and Z. We're very familiar with X, Y, Z. Okay, those are the three parts of a space vector. We're just gonna add this one. But four vectors are not the same as just slightly longer three vectors. Because it's the CT here, it even has different units, right? There's something fundamentally different about that time property. So I said, okay, we can write that Lorentz transformation going from one coordinate system here to a coordinate system that's moving. And I can move between them as long as I use these rules. So if you write that out, it gives you exactly what I wrote on the board over there on Tuesday. But notice that time goes at the beginning now. And there's this beautiful symmetry. So nothing happens to X and Y, right? When you see X2, don't think X squared anymore. Okay, we'll see the difference in that in a little bit. So this is now Y, and this is now Z. So this is not saying X cubed is X cubed, because that's garbage. It's saying Z is Z. Okay, that's not. Okay, and then you see how they're stacked like this. And on one side, you have all of these values. And on this side, you have a mix of those values in a funny way. And so in your mind, you should be thinking, or you'll begin to start thinking, that this is a system of equations. So if I'm solving a system of equations, then I get a vector on one side, and I get a vector of the other independent variables here. So independent variables, and this is the way that they relate. So this is the transformation matrix. Right? This is the tensor formalism or the matrix formalism. And I can simplify that by writing it in this format, where each one of this, so if this is 0, 0, then that would be this one. If this is 0, 1, then that would be this one. This is 1, 0, then that would be this one. And all I'm doing is I'm going along this line here, and I'm multiplying it by this. And normally I'll do this on the board with my arm, but if I'm using paper, I'll go like this, because otherwise you absolutely cannot keep it straight. And what's really important here is that the shapes matter. So this is 4 by 4, okay? And this is 1 by 4. So if I put this on the other side, it will not work, right? Because I always need to make sure I'm doing this like that. And if you have something disgusting, like say a 4 by 4 times a 4 by 4, and you don't know what that's going to make, you're still going to do the same thing. You're going to walk along, you're going to place this one in here. You'll notice, of course, that having this one on the outside, a 1 by 4, and a 4 by 4 collapses into a 1 by 4. So the order of the mathematics here matters. And that's why the order of this mathematics matters, because you end up with a different sized tensor. So here I have nu, and you note that there's a repeated index. So Einstein said, well, I don't want to write this symbol all the time. So anytime that there's a repeated index, that's the one that I'm going to sum over. And typically, if I have 4 vectors, which is everything that we'll talk about today, you're just summing over 0, 1, 2, 3. 0, 1, 2, 3. Okay. So that's the basis of tensor, and you'll get that at the beginning of Math Methods 2. It's using matrices, it's using everything that we learned in arrays, multiplying them into each other. We started this class talking about stuff that looked like this, and then we moved into stuff that looks more like this. And this dude's name kept popping up, Lorentz gauge, and that's a Lorentz transformation. And we're going to see how these. You may look at this and you say to yourself, huh, that's funny. Those are also 4 equations. So maybe we're gonna learn some fun stuff about how the underlying meaning of a lot of the physics that we've grown to know and love has been sitting just under the surface, waiting for us to understand it using relativity. Okay. So again, we have to kind of go back to 1912, when relativity was first came out as a manuscript. Of course, people knew about things like four vectors, and they were able to think about these mathematical concepts ahead of time. It wasn't like someone sat down and just had a eureka moment. That's never how science happens. It's a gradual building on one another. But Einstein's treatise on special relativity took all of these pieces, whether it's electromagnetism, whether it's dynamics at the time, whether it's the math of Minkowski spaces, and brought them all together in a way that was self-consistent that no one had done before. One of the first things that happened is, say, in 1909, Minkowski was able to show that if you have a three vector and you take a dot product, okay, something like this, A dot B, we're familiar with dot products, we like that. You just multiply the components in each direction. If you have a four vector, this type of four vector, one that has CT, not with a weird other fourth dimension that we're not familiar with, then it's the same stuff, A, B, and I'm gonna be a little careful here, so I'm no longer putting them at the bottom, I'm gonna put them at the top. I'm gonna do a one up here, but in your mind, you think X. And then this one, it's not a two, it's Y. And this is not a three, it's Z. Oh, shit. Fuck. All right, it's Z. Okay. And similarly, this is not a zero, it's CT. Very good. So that all looked good, right? We were having a lot of fun until the minus sign. So this is like, huh, that's weird. Wonder if that has any implications. Probably not, right? Okay. So we would think to ourselves, well, time is just another coordinate, nothing special about it. But in fact, we're already seeing something really important here, and that is it is treated differently. Okay, so let's look at the implications of that. We're going to build something called the invariant integral. Okay? Invariant integral means it won't be changing as I move frames. Okay? So this thing here we're going to call AA. And notice up here we are summing. So notice what I just did up there, that Einstein summation rule. I am expecting you to see A times A and two repeated mu's, one on the top, one on the bottom. And therefore you will be summing them. Now you may not notice this, we'll talk about this in more detail when it comes to tensor mathematics. Here the new, if you're going to sum over it, it needs to be one on the top, one on the bottom. And if you're going to end up with a tensor, you need to be left with the tensor in the superscript, not in the subscript. Okay. All right, so did this work? Yes, okay, so this is A1 squared plus A2 squared plus A3 squared minus A0 squared. Okay, all right. Learned nothing so far, just a lot of words. Good. So I am going to tell you, okay, that if this product is greater than 0, we call this space line. Okay, what do you think this one is? Yeah, very good. Why did you guess that? Because it's the negative, right? Good. So if it's less than 0, then this is the largest contribution, right? So that's timeline. What's this one though? Space-time like that was close, very close, but not correct.
Light like?
John, you're halfway there. What is it?
Oh, is it light like?
There you go. Right. Okay, so this allows us to understand something called the displacement for vector, and we can think of this in the context of how far away are two objects in space and time. Okay, so if I wrote that out, I would write it out like this. This is the invariant interval I, which is defined as delta x delta x like that. Right? Okay. Another way of writing this would be if you wrote out all of the individual components, but I don't want to do that. So instead, I'm going to say the distance in space squared minus c squared t squared. And now this should make a lot more sense, right? Okay. So what are we talking about? So I'm saying the invariant interval of what, Chris Martin, right? You're just saying words, it's early, it's late in the semester, no one gives a shit. Okay. So we always have to think about trains and moving objects, etc. So if we imagine two things, okay, like this falling over, this glass falling over, and your glass falling over, and they are separated by some distance. Okay. I can watch one of them happen and then the other one happen, right? Let's say my dropping the glass caused you to drop your glass. You'd say those were causally linked. We're gonna have to remember that, right? But if mine had no impact on yours, they happen to fall, say at similar times, one after the other. I could imagine a world in which, let's say I'm on a train, I could view them in the opposite order. So if this one fell for someone at rest, this one first, and then that one, there is a way for me to move between the two situations where I see that one fall first, and then I see that one fall second. What does that sound like? Yeah, so that's the first claim we made. We said that simultaneous events in relative frames are not necessarily simultaneous, that the ordering events is not sacred. Now, it is sacred for very special types of events, and we have to distinguish between those when we think about physicality, right? If I cause something to happen, right? If I make something happen, then the effect cannot precede the cause. Otherwise, you break physics, right? So they have to be unrelated events. Okay. So the definition here for timeline, let's do this one first. Now you have two events, they're separated. I can be in a reference frame such that they occur at the same point. Does that make sense? Okay, all right, it shouldn't make sense. We're gonna see a picture of that in a few seconds. Okay, so this would be a reference frame that's moving such that these two events occur at the same point, but not necessarily at the same time. Does that make sense?
It will be point like in the same space.
Yeah, so let's remember here, we're talking about an event happens at this cup and an event that happens at this cup. Okay? I can be at rest and I can clearly see that that cup falls over first and this cup falls over second. Okay. But I can also be in a uniformly moving reference frame because what we are talking about here are Lorentz transformations, which are transformations that are made into a reference frame that is uniformly moving left or right or up or down or whatever. But I can make a choice such that I could be moving at, say, half the speed of light, right? So that they won't happen at the same time, but in my reference frame, this happens at x equals 0, and then my x equals 0 moves, and this also happens at x equals 0, all right? So they would be time-like connected. Make sense? Okay. If, on the other hand, it's greater than 0, then they are space-like connected, and that means there exists a system in which they can both happen at the same time. If I'm moving between, or some other ways, right? And if you're special like this, then you're traveling like light. Okay. So let me show you the fun part, and then we'll get into the physics. So we get to draw your first Minkowski diagrams. Maybe not your first. Have you seen my Minkowski diagram? Space-time diagram?
Yeah.
Yeah. Okay. So typically, when I draw something like a ball, I throw it up, and it goes back down, what do I put on each axis? Oh, which one goes where? I'm on the bottom, good. And position or height maybe on the top. Right, so this is sort of standard, and let's say I want to trace the path of a ball, I'm gonna throw it straight up and straight down, no vertical movement. So what is it gonna look like? A curve, okay, good. And interestingly about this one, you have H and T, and that's kind of natural. So what is the slope in this type of a format? What's that? The velocity, right? So here, in this format, V is dH dt. Cool. Okay, so let's fuck that up, and instead, we're gonna put T up here. Good. Now imagine we're still in our one-dimensional world with the exception of time, so we're gonna put that here. Okay, so your first instinct here is gonna think that they're similar and they're not similar. Okay, because now instead of the derivative, it will be the inverse of the derivative that will give you the speed. And let's have a look here. Okay, that's T. Really, maybe I should change this a little bit. We could call it CT, or we could call this C, but let's do it. CT is the coordinate, right? So what is this?
A boundary?
If this is 45 degrees. What's that? It is a light-like curve. Here, what I'm looking at is at every instance that I move to the right, let's say some distance, that is equal to CT. So I have to be moving at the speed of light to get that far. Ah, okay, so let's draw this a little differently. Maybe I'll make this a little bigger. Okay. I have to be a little careful here. I'm not a very good drawer. Y'all know that. Okay. So let's say this is the present. This is time equals 0. Where is the past? Down. Good. Past. And this is the present. Present. And where's the future? Ah, you got it. Everyone's on it today. Okay. Future. Okay. And I'm gonna draw some lines here. That's your 45-degree angle. Even though it wasn't perfectly drawn first. And the claim was that these are light. Like intervals. So C equals V. Okay. So anything that I personally can get to, right? Let's say I'm in my train again, and I'm going half of the speed of light. I want to travel some distance away. It's going to take me some time. And so therefore, I'm going to have, because I'm traveling less than the speed of light, my path is going to be sharper, more steep, right? If I were able to go faster than the speed of light, it would be shallower, less steep. Okay. So anything that I have access to in my future is going to be on this side of the light cone. Now, we haven't called it a cone yet, but of the light triangle. So this is all bounded by the fact that I cannot move faster than the speed of light. So let's say an event occurs here. Can I access it? No, that's correct. Make sense? But what will happen instead is if I wait, okay, so this is my position. Let's say I go from here to here, and then I go back a little bit, and then I go over here. At some point, maybe up here, my light cone, which we can draw at every moment, and this will be perfectly drawn, now we'll have it in my past. You see? If you wait long enough, you can see everything in the past. Right? But currently, there's a lot of stuff that you can't access. You have to wait for the light to get to it. Right? That's the fastest thing that can send information. Okay. So we have drawn these in 2 dimensions, and of course that is incorrect because we don't live in 2 dimensions. So I gave away the game already, and that is that these are cones. That would be if you were to rotate this picture in this direction, so you had all the XY plane. You may be thinking to yourself, well, that's still not enough dimensions, right? And it's not. You want to think of this, maybe you don't want to think of this, but you should be thinking about this as a hyperboloid. So depending on what your speed is in this frame of reference, you know, where you're allowed to access. Let's say for you personally, you will always be space-like, right? You'll always be in here. And so you're gonna always have a surface that looks like a cone going up and a cone going down. Whereas someone else might not, depending on what the interval is, if you want to connect two different points in this space-time, that might not fit onto the same curve that you are. Okay. Okay. All right. The only thing that I think I really want you to take away from this is that the displacement of two events, right? In something like a space-like event is not absolute, and a time-like event is. Right? So that's the important thing we have to keep in mind for causality. So if one thing happens that causes something else to happen, they need to be connected by a time-like event. Does that make sense? Okay. So we've talked a little bit about how fun these cool vectors are. And I wrote this thing on the board. And you're like, wow, cool, velocities, those still exist, good. So what happens to velocity in a moving reference frame? Is it just? Yeah, so in a moving, like, so I guess the question is, let's say you're in a plane. Anyone been in a plane? Okay, so you're in a plane, and this is a very special plane, because it's going half the speed of light. Okay. So as it goes half the speed of light, you're really hungry, right? And you're wondering whether you should order something from the space, attendant, whatever they're called, flight attendant, but in space. So you're going half speed of light. And they say, what is it called? The flight person say, hey, this is your captain speaking. We are moving at half the speed of light. And you think to yourself, is that half the speed of light for us? Or is that half the speed of light for air traffic control on the ground? Because if he tells me that I have 40 minutes left on this flight, is that 40 minutes left for me? Or is that 40 minutes left for ground control? You see? See how it's a little complicated? Because what happens as we're moving in at near the speed of light, half the speed of light? What are the two things that happen to us?
Time moves slower
Time moves slower for who?
for the people on the plane.
People on the plane don't experience that. They will see the people who are standing still as their clock's moving fast. Right? We on the plane, we're gonna get hungry at the normal rate. But when we get off the plane, they're gonna be like, oh, it's been 2 hours. Okay, it's been 30 minutes. What are you talking about? So our clocks will appear to have run slower. Right? If we're on the plane. So you have to think about what the different reference point is. Okay, good. And what's the other thing? Length contract. So the first question we have is, well, what about something that takes both of these quantities, like a length in the top and a time in the bottom, and takes their derivative? How does that work? Yeah, they're both gonna vary, right? And so now instead of one simply moving and one changing as a function of time, we have to be very careful. Okay. So you're familiar with this one. This is what we call the ordinary velocity, because it's boring. And we're gonna call this the proper velocity. Eh? One symbol. Okay, so this would be, in this example. Okay. So this is called the proper time. This is the time that the person on the plane experiences. But this is the distance that you actually travel. So now we're gonna be, it's a little tricky, we're mixing some on the ground stuff with the stuff that the person experiences. But generally speaking, there's a nice little relationship between them. And we can write that the proper velocity. It's straightforward, it's simply 1 over the square root of 1 minus u over v squared. Like that, oh, nice. C squared u. You seen that before?
Yes,
What is that?
that is gamma.
Yeah. Cool. All right, so let's see if we can write this out. Generally speaking, you can write. You want this still? We didn't like it. It was fine. Didn't do anything for us. It's better. Minkowski diagrams are better when you have like, oh, this is black hole and you can't go through it. You're like, oh, that makes more sense how you got trapped forever.
So the cone instance is just adding on an additional dimension, and that would be like if we were two-dimensional.
Yeah, this is like if you're two-dimensional.
Okay.
And the reason that we treat it like we're two-dimensional is because in special relativity, we can always orient ourselves in the direction of motion. We just change the coordinate system. When you get to GR, it's harder. So we just, that's what we use in order to sort of understand it at the, don't want to say introductory or basic, because it's neither of those things, but at the first level, yeah.
What would you call that? The diagram?
That's a space-time diagram, or if you want to be real fancy with it, right, posted in IG, like Minkowski diagram.
Minkowski.
M-I-N, it's in your book. Okay, so generally speaking, we can write this, but you may be thinking to yourself, well, weren't we just talking about the fact that there's like different directions and stuff? So like you said X, Y, Z, and then like T and shit like that. So like, what? Okay, so let's write it down. So in fact, this is a tensor as well. And it looks like this. It's defined as DDT, DDT of X. Huh, cool. But it's not quite T. It's tau, the proper term. Not the ordinary term. So in general, we'll use 2 different words. We'll say on this side, these would be, and this is the transformation between ordinary coordinates and proper coordinates. The proper coordinates having to do with the ones that are undergoing the motion. So for us on the plane, these are the ones that we experience, versus these are the ones that air traffic control, or maybe your family in Missouri are waiting for you. Right? Yeah, or no? Okay. All right, so we can say something like this. And write them all out. Reasonable? And that's called the floor velocity. Okay, so this is what we call. Say to yourself, that is not satisfying. That didn't do anything for me and I don't get it. And it doesn't make any sense and I don't like it. Okay, so let's think about why would I want velocity. Because we're headed somewhere. I promise you one of 2 great, amazing things today. Right? It's the first thing I promised. E equals mc squared. Oh. So let's think about this for a moment. if I have the velocity, and I know how the velocity transforms, and more importantly, I know that you need to transform the velocity. So there is a difference as I move toward the speed of light, there is a difference between the velocity that I experience as a particle moving towards the speed of light and the one that you measure. There's a difference in the velocity. So there's a difference in the velocity. There's also a difference in the so I need to first describe things like momentum and energy. And then I can describe things that we care about, like force, which is the rate of change of momentum, and the work, right? How things are done by relativistic particles. Because unfortunately, I'll have to take all of this Lorentz stuff and re-derive Newton's laws. I'm not going to do any of the derivations because they suck. But you can find them in the book. No, they don't suck. They're just complicated. And no, they're not complicated. They're straightforward. There's just a lot of math. And I don't have the time, right? They're beautiful. Okay. But the implications are what we care about. So the first one is, how do we define momentum? MV, very good. Okay, but I'm gonna use the relativistic momentum here, because I want the relativistic momentum. I want the relativistic speed, so that I can get the relativistic velocity, so I can get the relativistic momentum. Okay, that may survive. All right. Boom. Right? No, yes or no? Okay, and really important that we go back to the definition, which is this one here, and we are going to see some fun stuff. Okay, MU. Cool, right? Wow, fundamental understanding of the universe. Nothing has happened, right? You don't care. This is the relativistic momentum. So this should tell you something sort of strange, perhaps. It's part of a 4-vector as well. And I can think about each one of these components. So if, for example, you know, I could write this up here, but we're not going to do it. Let's have a look at this really quickly and see if there's anything strange you see. Yeah, anything strange you see. This looked exactly how you expected it. I mean, I know you had no expectations going into it, but let's think about Newtonian mechanics, right? Let's imagine that you have a ball and you throw it. Yeah.
U is equal to C.
Okay, so interesting. So you're saying that as U approaches C, then this becomes 1, and 1 minus 1 is not a good thing to have in a denominator?
That makes sense.
Why?
You want to go super fast, you want to have a lot of momentum to stop you.
Well, but as I get going faster, the momentum goes to infinity. Yeah, well, you're not wrong, right? Because I would have infinite momentum, right? Like, that's pretty cool.
Don't we also,
If I could get something going near the speed of light, the momentum goes way through the roof. Fucking bonkers.
doesn't that also mean that like our mass would have to be exceptionally small the faster we go towards C?
Well, I haven't said anything about mass yet, right?
Ah, okay.
But if I could get something moving to 9/10 the speed of light, the momentum is gonna go off the charts. If I get it up to 99.999% the speed of light, right? The momentum is insane. But then working backwards from what you're saying is, how do you get it that fast? And to John's point, okay, If you're gonna use any reasonable amount of force, right? Then you better hope that the mass is small. Okay. Or, what did you say?
The light thing, massless?
Massless, what are you talking, there's no such thing as a massless particle. In Newtonian mechanics, a massless particle is abhorrent, right? It's disgusting. Right? How could something with mass ever deliver energy? Could never, right? Because think about it this way, what is a mass? What is the kinetic energy in Newtonian mechanics?
1/2 mv squared.
1/2 mv squared, correct. So let's say I have a massless particle, like you claimed, even though I don't believe it exists. And we're shooting it at some massless particle at something, right? It should not matter. It doesn't matter, right? Because it's massless. That's the claim, right? Good. And that's been the claim for 400 years up until this moment in 1910 that we are currently in. Good. But then someone comes along, German fella, and he says, maybe not so much. He makes a claim that momentum can be delivered by a massless particle. Which massless particle is that? Isabel already told us. Massless particle? No, it's not fine. Right? You went to one of his lectures early on, I'm sure. 1909, perhaps, right? 1910. So what's the massless particle? It has a name. The photon. The photon has no mass, and yet relativistic dynamics. We haven't even talked about electrodynamics. We haven't talked about electromagnetism. Simply from using that over there and taking a very detailed derivative, you have discovered that light is allowed to have no mass and yet deliver momentum. You haven't done an experiment. You see? That's the power of doing the Lorentz transformation correctly. That's the power of relativity, right? Okay, is this true? Yeah, it is true. I'll show you why in a few seconds. Okay, so this is, remember, it's still 1910, 1911, something like that, 1912. So they don't have computers, right? They don't have digital technology. They don't have the iPhone to take pictures of the board, okay? So they're writing this shit down. At best, maybe you got light bulbs, right? That's like your most common piece of technology. And yet they're describing this new phenomenology, which is the fact, one, that there are multiple forms of light that they didn't even know about until very recently. They're finding this stuff called radiation that they don't really understand, that's causing Marie Curie to get very sick, right? In a way that they don't quite understand. And they have not understood the interior of how stars work. So our main source of energy is the sun. And for hundreds of years, people have tried to calculate how much coal needs to be in the center of the sun. They have calculated how much TNT needs to be in the center of the sun. And they keep finding more stuff that blows up good. And they keep calculating how much stuff needs to blow up in the center of the sun. And they find out that the sun is either very young, like 8,000 years old, or it has something inside of it that we don't understand at all. No understanding. But they have rocks. And they know those rocks are very old, much older than 6,000 years. And yet the sun would have gone out. So they have no clue what the fuck is happening. Right? Okay. So here we have this thing, this massless photon that can deliver energy and momentum. Okay. So Einstein took the first piece of the momentum vector, P naught. Okay, this one here. And he said, I'm going to multiply it by C. And that has units of energy. That is the relativistic energy. This is the energy that exists when something is moving near the speed light. Okay, so let's look at that. E is going to be written now as mc squared over the square root of 1 minus u squared over c squared. God damn, we almost got it. We almost got to the big one, right? That's not it, though. That's not it. Is it?
Why can you change one U to C but not the other one?
What do you? This one here?
The U and the numerator.
Yeah, so, what we're talking about here is the relativistic energy of the system. So the U is gonna be down here. The derivation, I can show the derivation later if you want. No? Okay, all right. Okay, that doesn't have, this is not the kinetic energy. This is the relativistic energy. And in particular, if U is 0, what do you get? Right. So the thing that you're all familiar with is actually the rest energy. And that is m squared. When U. Okay. So before I show you what the total energy is, let's think on that for a moment. Okay. So there is very profound implications, especially for us as physicists, right? What is the most profound implication of E equals mc squared? That mass and energy are interchangeable. At the time, mass was conserved quantity. 1910, you didn't make mass from nothing. And the claim was that in fact, nope, that's garbage. I can make and destroy matter as long as I account for the energy. Right. And because this is multiplied by c squared, you get some good quality out of it. If you get a gram and you multiply it by c squared, you get a lot of energy. Okay. And in fact, this is the first piece to understanding nuclear fusion, nuclear fission, right? And of course, one of the things that happens in 1910 is that scientists, physicists, who are sort of impressed, amazed by this, go straight ahead without thinking of the ramifications. Never think about the ethics of what they might be studying and develop the nuclear weapon, right? Which as a community, we should all understand the significant ramifications that happens when we just barrel ahead without thinking of the ethics, right? Millions of people die. Okay. So in this particular circumstance, something so beautiful, something so illustrative of the underlying physics of the world can actually be quite dangerous. You hand it over to Raytheon or an atomic lab. Okay, something to keep in mind if you haven't watched Oppenheimer. I've heard it's good. I haven't heard it. I haven't watched it myself. The story of Oppenheimer is one that every physicist should remember. Right? He developed the atomic bomb and then spent the rest of his life trying to undo his life's work. Right? And that should tell you how serious this type of work is. Generally speaking, I think we've come a long way. Lots of people aren't dropping atomic bombs anymore, but it's not good out there. Okay, so in fact, this relativistic energy is part of the energy momentum for vector. And it looks like this. P mu. Okay. I wrote that is the energy momentum here. The kinetic energy, it goes like 1/2 mu squared. Let's see if I can write it. Everyone knows that second term. Okay, so this is the kinetic energy, which of course is the 1/2 mv squared, as we all know and love. But there are higher order terms that come from the expansion of this into terms of u. Okay, so the 1/1 minus u squared over c squared, you can use a Taylor expansion to break into that. And then, of course, when you subtract the rest energy, you get the kinetic energy. So this is the total energy. That's the rest energy. Okay. Generally speaking, you have an invariant quantity, which looks like E squared minus P squared C squared equals M squared C to the fourth. That is the conserved quantity in terms of momentum and energy. So I can turn mass into energy, energy into mass using that boy right there. Okay, in a closed system. And this immediately tells us that you can power the sun, because now I can just change mass into energy. We predict nuclear fusion. Let's go back to Isabel's so-called photon, which I'm still not sure exists. I don't know if I believe it yet. What is the energy of the photon?
Zero.
What?
We go by that at zero because there's like half part.
Well, this is 0. But that means that I can put PC on the other side. And there's a direct relationship. What did I just put down? There's a direct relationship where E equals PC, right? And in fact, one of our friends, good friend, Planck, has been shouting for a long time that the momentum has something to do with, you guys know that one? No? Yeah, so according to the Planck formula, he says that the energy is h nu. Okay. And so therefore, they are different photons and they can have different energies despite having no mass. And it has only to do with the frequency of the light. So apparently, according to him, the claim is that higher frequency has a higher energetic content. So blue light is more energetic than red light. Good. That's the you can be bothered by all this, you not care, that's fine. But you may be asking yourself, why the fuck are we learning? So let's go back and we want to think, now we have energy, we have force. We didn't really see force, but I promise it exists. We have Lorentz transformations, and I want to pose to you 2 thought experiments. Okay. Maybe I won't make a thought, maybe I'll write them so they're not so confusing. Okay. The first one I want you to imagine is a line of charge. Okay, and it's going to be moving to the right. And it's going to have a positive line of charge, so individual pieces of charge or whatever. I'll draw the picture in 1 second. And then also let's say if we have 1 positive, we'll have 1 negative going the other direction. Let's imagine plus. And these are all headed towards the right. It's velocity v. And these are negatives. So much easier to write. And then they're going to the left. Okay. You seen this before? You know how to solve E and B? Come on now. Come on now. Okay, good. All right, so we have a lambda here, we're gonna go minus lambda here. Lambda is the unit length of charge, right? Yeah. And now let's take the charge. Here's our friend Q. And he's moving, but he's moving with a different velocity. He's gonna be moving with U. And that's V and that's U. And there's some distance here. S. All right. So what does Q experience?
The
Good.
charge.
That's correct. Of course. That's correct. And why? Por qué why?
Next to a wire.
Y and E field. Let's work through it together. So I'm here, I'm living on this charge. I'm moving, or sorry, I'm here looking at this and I'm watching the charge go by and I'm calculating what the force that I think will exist at S that the Q is moving. Is there an E field? Let's do Gauss's law really quickly.
Yes.
What's that?
There's no electric field outside.
There's no electric field outside because the charges are canceled. We have a net zero charge. So Gauss's law says there should be no E field outside. But I have what? A B field because there is a. Yeah, there's current, right? So the moving charges here, I have I going back this way, but they're all negatives. So it's almost like 2 plus net charges going that way. Oh, yeah, sucks, right? Okay, so in fact, we do have a B field. And this thing's moving. Ah, so I have a V cross B, so the thing's gonna move.
Yeah.
And so everyone in the household agrees that this is a. No. Everyone in the house agrees, what kind of force is this? This is a magnetic force. It's a B cross V force.
Yeah.
Right? Because there was a B field and this is a moving particle. So the reason that this thing is deflected has only to do with the presence of magnetism. And everyone agrees, right? Okay. So you know this is a trap already when I talk about this. All right, so now let's become the charge. Now we're moving along to the right with the charge, and therefore, in that new frame, what do I see? Well, if I'm moving along with the charge, then there is no velocity. And this is gonna be a new velocity, V plus U. And this is a different velocity, V minus U. Particularly if this is relativistic, as this moves to the left or the right, the charge per unit length is going to change. Okay. So now let me ask you a question. You're not moving, this thing's moving. Okay. Is there a force?
No, it's just-
Let me ask you a different question. Let's look at we're thinking about this, is this the right way to have set the charges when they're moving to left and right like this? So V minus U is going to be smaller than V. So now the charges should be packed closer together, right? Whereas V plus U is going to be larger, so now they're going to be dragged farther apart. So let's do this. Let's draw this properly. So in this new frame, the charges don't look like that, but they look like this. Wait. I'm trying to be a little bit better here, but I'm bad drawing. And the pluses here are going to be drawn out because it's moving very fast to the right. All right. So now, go ahead.
It's an electric force.
Now there's an electric force. Whereas before there was a magnetic force. And now there's an electric force. And the charge in that current or that wire or whatever we want to call it, no longer cancels out. So where we used to have a wire which was electrically neutral, now it's no longer electrically neutral. That's stupid, right? So who's right? Is it an electric force or a magnetic force? What'd you say? Yeah, both. You're right. What do you think this is? Communist America? No, it's not. It's not both right. Only one person's right.
Well, it depends on where you look at it. Where the observer.
Woke kids, everyone can be right, everyone magnetic. No, that's not correct. I'm joking, of course, that is right. So in one reference frame, you see magnetism. In another reference frame, you see electromagnetism. A little bit of electricity, a little bit of magnetism. Who can say who's right? There is no preferred reference frame, right? Because that was the fundamental claim of relativity. That inertial reference frames, one that are moving at constant velocities relative to one another without undergoing accelerations, are all identical, and all the rules of physics should be identical. So the total force that this particle feels will be the same in both reference frames. But the causes, our interpretations of them, E or B, or a combination of E and B, may differ. Weird, right? Yeah, so that's the first cool part. It gets cooler. What if you have a capacitor? More capacitors. Okay. Okay. Let's say you have a capacitor. You remember what capacitors look like, right? That's a really good drawing of a capacitor. Stop. It's a good drawing. Okay, there's minuses on the bottom and there's pluses on the top. It's a parallel plate capacitor. Two plates, it's a good capacitor. Okay. All right.
2 napkins.
Good. So what's the E field here?
It's like straight down from positive to negative.
Good, bingo, right? Straight down, and we found that was fine because, in general, it was straightforward because there's no other directions. No other reasons for it to go in any other direction. Right? So you're like, obviously. Okay, now let's move. Okay, so let's move the entire system in X. Okay, what happens to the fields? Are you showing me how the field moves?
No.
Oh, okay. So I didn't know how to interpret your hand motion. Yeah, the whole capacitor is gonna now move to the right, and remember, these are relativistic capacitors, so they can move half the speed of light by magic. What?
I guess we're gonna get some sort of B.
No. Not vertical, yeah, but why? Well, let's ask you a couple questions here. What are the physical things that happen? Remember, we always have to go back to the physics. So the object moves from left to right at relative velocities. What happens to the plates? They start off as square, they stay square. They scrunch.
Moving that fast.
Yeah, these are relativistic plates. Oh God, right? So they're gonna squinch. Okay, as they squinch, okay, what happens?
Field gets more intense.
Why?
It's not.
Close, but you almost got me, but you haven't explained why.
Still not-
What is the field of a capacitor?
Oh, surface charge sigma.
Over A.
Oh, epsilon something.
Over A.
Sigma, remember, sigma is already Q over A, John, so you were half right, but sigma's already got the Q over A. Okay, so now what happens as the plates get triggity?
They squish,
They squish, and then surface charge goes
squish.
up.
Also, the field gets more intense.
Okay, so in fact, only the component of the parallel field changes, and we can say something like E perpendicular is equal to gamma naught E naught perpendicular, whereas E parallel is going to be E. Okay. I think that's time. Okay. You could then think about the fact that the charges are moving and that there is magnetic field and blah, 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 blah. I'm not gonna be able to write all of the transformation here, but I'm gonna show you how the fields transform. And then I'm gonna give you the crescendo of the entire course, okay? If we can make it. Right, culmination, of everything you've ever wanted to learn. Okay, so let's do. Fuck this, not to us, it's dead. I don't even like it. Okay, fields transform. And the E and B fields are not going to transform in the ways that we are comfortable with. Because they're not really friends in the same way that we think. So before, you know, like the contractions were in the direction of the motion. And X and Y, or sorry, Z and Y, we didn't really care about. That's not how it works in real life. Okay. So in general, we say something like E. And I'm gonna put a little bar here to show what the transform versus the untransformed coordinate is. So if I'm moving in X, then nothing happens. To E or B. Cool, right? But if I'm moving in X, then I'm gonna get this stuff. And this is the stuff that's really fun. Okay, it's gamma. Notice the symmetry yet? No, no one notices anything, right?
Oh, the one over C squared, relationship with B and E. That,
Oh. I need to write, there's too many letters that I can't understand. I shouldn't ask the question. My bad. Okay. You see any symmetries? Yeah, it kind of looks like it could be similar to a 4 velocity. I got 6 equations here. I'm a little cranky about that. But I'm gonna do my best. Okay. And in particular, these transformations are still going to be right for when we discuss, like, if you look at E, V cross B, you'll get them all back. They'll be fine under that transformation. So let me just write for you electrodynamics in vector notation. So you can write this as an array. Okay. Shit, I don't know if that's- Yeah, I get that. F U naught B is a 4 array. 0, 0, 0, 0. So that's one of them. And there's another one. These ones down. If there's anything put written down at the beginning of class, not that crap, it's this crap. Yes, correct. Boring, okay. Lost you at the end, everyone's asleep, okay. All right. So generally speaking, we can write these as field tensors. And these are going to be the relationships that transform our E's and B's. As we go back and forth. So if I write them in this format, you'll see that there are some fun properties of these. You may think of them, this is the dual tensor. You don't have to have memorized. And these are both anti-symmetric second rank tensors. Okay. So what does this actually look like in practice? Well, we have to think about one more 4 vector. And that is the one that we haven't been talking about. That's this guy over here. There's a fun relationship between them. J's and rows are part of the same family. So I can always write J0 is going to be C row. J1 is JX. J2, JY. Is that a J? Yeah. And that's JZ. Yeah. Okay. So if we write it that way, then we can write a couple different things. So for example, you can write the continuity equation. You remember the continuity equation?
Oh, negative change of row over time.
But now it's not that anymore, it's just this. So because I'm using a tensor format, because I'm using a new 4 vector format, in one stroke, I can demonstrate that the charge and the current are conserved. That they move through space and time together. And we already knew that. Currents are moving charges, right? So that's not something new, that's stupid, Chris. Okay, so how do I write thing that you really care about? Well, now that I wrote our axisymmetric second rank tensors, we can use them with our new 4 vector. So this is the new 4 vector. Doesn't have a fun, current density. Four vector. That's the name of it. And so you can write Maxwell's equations. So this is Maxwell's equation right here. Obviously, right? Okay, that doesn't look better. And you might say to yourself, it's just as good as we were doing over there, but I can understand those ones. Those at least make sense. But these ones are variant. So what I mean by that is as I move around, as I transform from one place to another, whether I'm in the reference frame of a moving particle, or if I'm in the reference frame of the detector, which is going to measure the radiation from the moving particle, I don't have to rewrite the equations. They're already written like this, and they're self-consistent. Okay. So if I can just find the 4 vector, then I can find the dual tensor that gives us everything we want. But generally speaking, you're still not satisfied. You hate it, right? You're like, we haven't learned anything. It's still stupid. Okay, so the last 4 vector I'll give you, and then you can be free of me for the rest of the semester, is the best 4 vector of them all. Okay, and that is the fact that we had a scalar and we had a vector potential. You may be thinking to yourself, time is a scalar Doesn't have a direction, except for now you started making this weird diagram with the fucking direction on it, but all the rest of those are vectors. And similarly, you know, you said the momentum here, relativistic momentum, that is a vector. And the time has a scalar component to it. So that is the same property that holds true for potentials. And in fact, we can create the 4-vector potential, which is A mu, and that is simply V over C. This is the vector potential now, comma AX, AY, AZ. Cool, you're like, that doesn't mean anything, who cares? No one cares. Okay, I can rewrite the field vector in that same context. So this is the field vector here. But if I use this and the D'Alembert, then Maxwell's equations are very simply that's it. Okay. So no like round of applause, no cheers, okay? No one understands what the fuck that is. Who cares? What's the point, right? But this begets an underlying truth about the universe. That electricity and magnetism are not different forces. The reason that we say electrodynamics, the reason that we say electromagnetism is that the force that controls the compass is the same force that causes your hair to stand on end. Viewed from different reference frames. The only thing that matters, the only thing that connects them is A, and the distribution of charges and how they move. So the underlying force, the unification of forces, is when you can bring it all down to a common root. And the fact that you can do this at all is exceptional, right? Now, there are people who right now are very interested in unification of all 4 major forces. So we know gravitation and electromagnetism, they don't really have a common thing that they like to do. They behave very similarly. And that's because the way that they have an influence on the world is similar. They influence the world through very similar types of fields. You have 2 other forces, fundamental forces. You have the weak force, which controls the decay of the inside of atoms. And you have the strong force, which holds together quarks. It turns out that you can take this a step farther when you combine it with quantum mechanics, and you will find out that electromagnetism and the weak force kind of friends. It's a symmetry that you can exploit to show that that's a coupled set of relationships. Right? And so what people are working on and what they've been working on for a very long time is to bring this into the fold with what you essentially would think of as the strong force, make them talk. They've worked on that, they've completed that. And now the last one is to bring gravity and make gravity make sense at very small scales where it doesn't like to make sense. Okay, so now you won't need aliens anymore, right? Because you have access to real special knowledge, unique knowledge that you don't even necessarily get yet, but you have access to understanding, right? You've earned that by learning just a little bit of tensor math. And a lot of it, you know. Any questions?
Thanks.
Okay, no homework for next week, but turn in all your stuff and make a time to check it with me. Other homeworks here? Yeah.
Can I turn in like a few hours?
I don't know, any?
Are you gonna be here?
Yeah, be fine.
They will be everything except for, let's say, where. This is my next one, right? Is that, or is that just a map?
Yeah, no, that's the moment of the that.
Yeah, so I was just trying to find this, so I got this here, and then this is current, and I'm just like, oh, we're doing a power. So we have this.
Give the resistance, right?
I don't think we do, or unless I misinterpreted something,
Double check.
because I don't think, because we were told that it's a radiant power, but not of like any material, so I can look up, their resistance.
This is 1123.
Yeah. And it's like, oh.
I have to double check what the actual work is here. The radius is 6, the.
I like it. It's like this stuff.
Magnetic diameter. Leave it with me, I'm gonna double check your work,
Okay,
just to make sure that everything is written properly, but.
Yeah.
I mean, you've done well.
thank you.
Bye.
Yeah, bye.
Would you be perhaps available to me?
For.
I'll show you.